Okay, so welcome everyone. So this is the week 5 problem solving season week 5 for the course Introduction to Rings and Fields. And I am Siddhartha Pramanik, and I am a research scholar from the Department of Mathematics, IIT Kharagpur. So before solving some problems, you guys, do you have any doubts regarding the assignment problems or the content of previous weeks? So if you have any doubt, you can just put it in the chat box. Okay, so let me start the session. Meanwhile, you can ask anytime in between the session. So I will just summarize the contents of week 5 first. So in week 5, we started with the proof of Hilbert basis theorem. So which states that if you take a Noetherian ring R and if you take the polynomial ring over that ring R, then the polynomial ring is also Noetherian. Of course, you have to take finitely many variables. So that is the Hilbert basis theorem. And then we started with divisibility in integral domains. And for that, we have introduced irreducible elements, also prime elements, and after that we have saw some properties of PIDs. So let me just write down PID. And after that, we have defined UFDs, and we have saw a couple of results related to UFDs. And okay, that's all. So these are the contents of week 5. Okay, so Hilbert basis theorem. So let's start with the converse of Hilbert basis theorem. So so let me write down this as true or false. So converse of Hilbert basis theorem is true. So so we all know that Hilbert basis theorem says R is Noetherian. That will imply the polynomial ring Rx is Noetherian. Right? This is the Hilbert basis theorem. So now I am asking about the converse. So if Rx is Noetherian, then can we say R is Noetherian or not? So what do you think? So let me write down the statement. So Rx is Noetherian implies R is Noetherian. So is it true? What do you think? So try to recall the results which has been proved in the after just defining the Noetherianness. So if Rx is Noetherian, so that will imply that any quotient is also Noetherian, right? So from this we can say Rx mod the ideal generated by X is Noetherian, and this is actually the ring R. So since R is isomorphic to Rx mod ideal generated by X, so it is Noetherian. So that means this statement is true. So the converse of the Hilbert basis theorem is also true. So that is something you should remember. Okay. Now let's study a couple of properties of the ring ZX. So we all know that Z, it is a PID, right? And PIDs are Noetherian. So Z is Noetherian. So by Hilbert basis theorem, ZX is also Noetherian, right? And so what Noetherianness means is uh, uh, every ideal is finitely generated. This is the one condition of Noetherianness, and the other one is every ascending chain of ideals eventually stabilizes, right? So this is the second condition. So this would be true in ZX also. But in ZX we have one interesting property. So let me write down it here. So that for each positive integer n, uh, there exists a chain. Okay, let me write ascending chain. There exists an ascending chain of ideals like a0, sorry, I0, I1, and up to In. And this is strictly ascending. There exists a strictly ascending chain of ideals like this in ZX. So however you take whatever integer, positive integer you take, uh, this might be very large, but still you will get an ascending chain of that length, right? So this n can be very large, but there exists an ascending chain of length n. So can you construct an ascending chain of ideals which satisfies this property? So did you understood this statement? Okay, let me write it as length n ideals of length n in zx. Okay. Okay, so we are in zx, right? So let's take in as the ideal generated by x and 2 to the power n for all n greater than 0. Okay, something. Okay. Okay, then uh, what is your I and I0? You just take ideal generated by x. Then you can see that ideal generated by x is strictly contained in ideal generated by x comma. Okay, we need to take the other way. Okay, you take ik is 2 to the power n minus k for k greater equals to 0. Then ideal generated by x is contained in 2 to the power n, and it is also properly contained in 2 to the power n minus 1. It properly contains in 2 to the power n minus 2, and you can go up to x comma 2, and we know that ideal generated by x comma 2 is maximal ideal, so it cannot go beyond that. This is our I0, this is our I. Okay, there is missing term, so n minus 1, so this would be n minus 1. Yeah, I think now it's okay. So this is our I1, this is our I2, this is our I n minus 1. So this containment is proper, so these two cannot be equal, that you can check, because 2 to the power n minus 2 cannot belongs to ideal generated by x comma 2 to the power n minus 1. So this is something you can check by contradiction, and this will give you the example. So I hope this is okay. Okay, let's move on to another problem. So zx is Noetherian, so that means every ideal is finitely generated, right? But uh, for okay, so we need to find an strictly ascending chain of ideals and which has length n, right? So I am just giving a particular example of that chain of length n. Okay, this is length n minus 1, so that's my mistake. So I think here you need to take x comma 2 power n. So this is I2 and this is I3, this is I1, and here you need to take if you put 1, then you need plus 1. So I am claiming that this chain is an strictly ascending chain of length n. So strictly ascending means we have this proper containments. So you just need to check that these containments are proper, right? So how you will check that? That okay, let me write it down for one case. Now x comma 2 power n is proper subset of x comma 2 power n minus 1. So how you will check that this is proper subset? So you just check that 2 power n minus 1 does not belongs to this ideal. So that is something you can check. So if you can check this, then you will get this proper containment, and this is same kind of trick you can play in all other containments. So this will give you an strictly ascending chain of ideals of length n. So is it okay? Okay. So now I am saying that every ideal in ZX is finitely generated, right? But for every positive integer n, there exists an ideal, let's say in ZX, such that in is generated by n elements, but it cannot be generated by let's say n minus 1 elements. So you can take arbitrary large n, then you can find an ideal in which is generated by exactly n elements. So if you take less than n elements, then you cannot find any generating set for that in. Okay, so this in this statement I will just give you the example. So let me write down it here. So you just take in as the ideal generated by x comma 2, and you just take its nth power. Okay, then you have to verify that it cannot, it is exactly generated by n elements. That is easy to see because it is like x power n uh, 2 times x power n minus 1, 4 times x power n minus 2, and so on up to 2 to the power n. So you will get n generators, or maybe n plus 1. There is something, one index might be uh, less than, but it cannot be generated by less than n elements. Okay, so that verification I am not going to do because it involves some other results. So you just take it as information. So so you just remember this statement. Okay, so this is true for ZX. Okay, let me write down some more facts, then I will come to some concrete problems. So let me just write down as fact. So this is true for any ideal, but if you take prime ideals, then this statement need not be true. So in ZX, if you take any prime ideal, so every prime ideal, so every prime ideal in ZX is generated by at most two elements. Okay, so in ZX, all prime ideals are either principal ideals or it is generated by two elements. So these are the forms of prime ideals in ZX. So just remember this fact. So you might see this in other courses like commutative algebra or maybe algebraic geometry, but let's not worry about that. Okay, so every prime ideal in ZX is generated by at most two elements. So I want to come to maximal ideals in ZX, but before that I need some other results. Okay, so let's prepare the background for that. So one more fact I need. So let R be an integral domain. Okay, uh, and let's say fx belongs to this polynomial ring Rx, be a polynomial of degree, let's say n, which is positive. Okay, then fx can have at most n roots in R. Okay, so this is about the number of roots of a polynomial in the polynomial ring Rx. So where the base ring R is an integral domain. So if you take a polynomial ring which is an integral domain, and if you take a polynomial of degree n, let's say fx, then that polynomial can have at most n roots in R. Okay, so this is a well-known result. So you should know this. The proof is also not difficult, but I don't want to go for the proof. You will find this proof in any standard text. So did you understood this statement, or do you have any doubt? Okay, I hope it's okay. So let's come to the next problem. So it is problem number 4. So let fx be a non-constant polynomial in ZX, then prove that fx takes infinitely many values in Z. Okay, so if you take any non-constant polynomial in ZX, then it will take infinitely many values in Z. So what does it mean? So f is a polynomial, right? So so we can treat f as a function from Z to z, so then image of f is a subset of this z codon. So f of x takes infinitely many values in z. That means this image of f must be infinite. So we need to prove the image of fx as a function from z to z is an infinite set. So up to this, is it okay? So did you understood this statement correctly? Means, I mean, it is clear from this. Okay. So how to prove this? So to prove this, I will use this fact. So let's write it here. So suppose fx takes only finitely many values. Takes only finitely many values in z. So that means image of f is a finite subset of z. So here if you take z, and here also if you take z, this is your function f, and in your image only finitely value points are there. So in the domain there must be infinitely many points which maps to a single point, right? Means which have the same image. So there must exist uh, a belongs to z such that f of n equals to a for infinitely many n in z. Okay, so that is the meaning. Okay, now you just take another polynomial, let's say gx. It's defined by f of x minus a. So then this is also a polynomial in zx, and this has the same degree as f of x. Okay, so then g of n equals to f of n minus a, and this is 0, and this is for infinitely many n. So this is true for infinitely many n. So that means this polynomial gx has infinitely many roots. But this cannot be true, right? Because a polynomial of positive degree can have only finitely many roots. So that means this cannot be a polynomial of positive degree. So gx must be a zero polynomial. So that means g of x equals to 0. So f of x is equals to a. So that means fx is a constant polynomial. But this is a contradiction, right? Because in the statement itself we have assumed that fx is non-constant. So this cannot be true. So what we have assumed is wrong. So we have assumed that fx takes only finitely many values. So this cannot be true. Thus, fx takes infinitely many values in z. Is it okay? Okay. So, if it is okay, so let's do one interesting problem using this problem. So it is problem number 5. So again, let f of x be a non-constant polynomial non-constant polynomial in zx. Then prove that the ideal generated by fx cannot be a maximal ideal. So it cannot be a maximal ideal in zx. So any principal ideal in zx which is generated by a non-constant polynomial, it cannot be maximal. So this is what this statement says. So in zx there cannot be any principal maximal ideal which is generated by a non-constant polynomial. So how to prove this? So first of all, fx is a non-constant polynomial. That means fx takes infinitely many values in z. Now fx takes infinitely many values in z. So that means image of f is infinite. It's an infinite set. Right? So that means there must exist an element in the image which is not equals to -1, 0 and +1. So, or more clearly, so there must exist, so since it is an infinite set, so image of f cannot be subset of this finite set. Right? So that means there exists a belongs to image f such that a does not belongs to -1, 0, 1. So let me write it here. So there exists an integer a or say n. There exists n belongs to z such that the image is not equals to -1, 0, 1. So in place of, since a belongs to image of a, so it must be must have a pre-image. So let's that pre-image be n. Now take the ideal I which is generated by f of x and f of n. So we have to prove that this ideal generated by fx is not maximal. So that means between this ideal and between the ring, so if you take the ideal and if you take the ring, so there must be some other ideal which contains properly. So my claim is I is properly contained between these two ideals. So claim ideal generated by fx is proper subset of I and I is proper subset of zx. So that will prove that ideal generated by fx cannot be maximal. Okay, so let's prove this proper containment first. So ideal generated by fx subset of I, it is clear, but we need to prove it is proper subset. So why it is proper? Because the element f of n does not belongs to ideal generated by f of x. And why it is? Because if f of n belongs to ideal generated by fx, then that will imply f of n is equals to fx times hx, some polynomial hx. So you just compare the degree of both sides. So here it is constant, so degree is 0, but fx is non-constant. So here degree must be positive. So this cannot be true. Since fn does not belongs to fx, so that will imply this proper subset of I. So this proves this first proper subset. Now let's focus on this one. So now if I equals to zx, then what happens? So that will imply one must belongs to I, and I is equals to ideal generated by fx comma f of n. So that means one must equals to fx times some gx plus f of n times some let's say hx. So for some gx and hx in zx. So now if you compare the constant term, so left side is a polynomial, right side is a polynomial. So you just compare the constant term from both sides. So by comparing the constant terms from both sides, so what you will get if you compare the constant term? So degree of fx is okay, it does not matter. So from here you will get a constant term, and here if you will get a constant term. So 1 equals to, let's say it is f0 g0 plus f of n h0, where f0 g0 and h0 belongs to z. So from this what can you conclude? Okay, am I doing something mistake? Yeah, you don't need to compare. Okay, so left side is a function, right side is a function. You just evaluate these functions at n. So by evaluating at n, we get 1 equals to f of n times g of n plus f of n times h of n. So this you can write f of n times g of n plus h of n. So this one is an integer, this one is an integer, and this is 1. So that means f of n must be a unit. So this means f of n is a unit in z. But what are the units in z?
1 and -1.
Yeah, so that means f of n equals to either 1 or -1. But if you see, we have taken fn is not equals to -1, 0, 1. So this is a contradiction. So our assumption is wrong, and which was I equals to zx. So thus I is also a proper subset of zx. And this proves our claim that I is properly contained in between this ideal generated by fx and the ring zx. So ideal generated by fx cannot be maximal. Hence, ideal generated by fx cannot be a maximal ideal in zx. So, is it okay? Okay, so I hope all of you understand this proof. So, a non-constant polynomial in zx cannot generate a maximal ideal. So, from this we can say something more. So what happens if we take a principal ideal in zx generated by a constant polynomial? So if n belongs to z, then the ideal generated by n in zx. So what can you say about this? Can this be a maximal ideal? So I think I have done this in the earlier sessions. So the ideal generated by n in zx is not a maximal ideal. This is because, okay, let me write down it here. So this is because zx by ideal generated by n is isomorphic to z mod nz of x, and this is polynomial ring. This cannot be a field, so this ideal cannot be maximal. So the constant polynomials also does not generate maximal ideal, and non-constant polynomials also does not generate maximal ideal. So that means maximal ideals in zx cannot be principal ideals. Okay, so principal ideals in zx cannot be maximal, or the other way you can say. So, do you have any doubt? So, we can say something more. So, we have already mentioned that every prime ideal in ZX is generated by at most two elements, right? And maximal ideals are also prime ideals. But maximal ideals cannot be principal. So, every maximal ideal in ZX is generated by exactly two elements. So, let me also write this. So, maximal ideals in ZX are generated by exactly two elements. So, I think I have done enough problems in ZX. So, let's move on to another problems. So, problem number 6. So, the other things which has been taught in the week 5 are irreducible elements, prime elements, UFDs and PIDs. So, let me write down the problem. So, it is again true and false. So, first one is subring of a PID is again a PID. And second one is subring of a UFD is a UFD. So, are these statements true or false? Just think for a few moments. So, you are saying no. So, do you have any counter example? So, why do you think? Okay, that is only a message. So, what do you think? It is true or false? No. So I think you are saying it is not true. So try to think of some counter examples. QX is a PID, but ZX is not. Yeah, you are right. So first one is false. So we can take your example. QX is a PID, but ZX is not a PID. Yeah, fine. So what about the second one? So the ring ZX has so many interesting properties. So that is something useful. Okay. What about the second one? Subring of a UFD is UFD or not? So I thought you guys will give some more easy example than this. Okay, so any guesses for B? So in the lectures, uh, I think this has already been proved that z root minus 5 is not a UFD, right? But it contained in a field. Z root minus 5 is subset of C, and C is a field. So it is field implies PID, and PIDs are UFDs. So this is also false. So you can take this example also for the first one, right? So subring of a C can be anything. It can may not be UFD. Okay, I hope you guys understand this. You guys can understand. So we have done the subring. Now what about the quotient? So okay, let's not write quotient. Let's write homomorphic image. Homomorphic image of a PID is a PID, and homomorphic image of a UFD is a UFD. So what do you think about these statements? Yeah, any answer? So homomorphic image means, so if you take an homomorphism phi from R to S, so homomorphic image of R means it is just image of this phi. So image of R under some homomorphism that we call homomorphic image. So okay, what you are saying? You are saying true. Okay, let me see. So true for one, first one or second one?
First one, sir.
So you are saying homomorphic image of a PID is a PID.
Yes.
So actually this is not true. So first of all, homomorphic image of an integral domain may not be an integral domain. So from that statement we can say that both are false. And the reason is homomorphic image of an integral domain need not be an integral domain. So you can take the example phi from Z to Z mod nz. So this is surjective homomorphism. So phi of Z is Z mod nz. So homomorphic image is Z mod nz. And this need not be an integral domain. But if we assume that the homomorphic image is an integral domain, then what can you say? Okay, let me write down as remark. So first one is homomorphic image of a PID. So the best you can say is it is a principal ideal ring. So homomorphic image of a PID is a principal ideal ring. That means every ideal is generated by a principal. Uh, every ideal is generated by a single element, but it need not be an integral domain. So it need not be an PID. So the best you can say it is principal ideal ring. So this is something you can prove that if your domain, so if you have an homomorphism phi from R to S and R is a PID and this is surjective, so S is a principal ideal ring. So that is something you can easily prove. So you just try to prove this. And and in the second case, so yeah, so in this case, so if we assume that homomorphic image is integral domain, so integral domain plus principal ideal ring is a principal ideal domain. So in that case, it will be true. But what happened in the second case? So assume that homomorphic image of a UFD is a domain. Then can you say it is an UFD? Okay, let me write down. Then you can think. So assume uh, phi from R to S is an onto ring homomorphism where R is a UFD and S is an integral domain. Then can you say that S is a UFD? So in case of PID, this statement is true. But is it true in case of UFD? So did you understand this statement? So we are just taking an surjective ring homomorphism where the domain R is a UFD and this codomain is an integral domain. Then can you say S is a UFD or not? So did you understood this statement? So here R is an UFD and S is the homomorphic image which is an integral domain. So in this case, can we say S is a UFD or not? So in this case also we cannot say S is an UFD. So the answer is not necessarily. So you can take, I will give two examples. So you can take Z to Z mod PZ. So this is surjective ring homomorphism and Z mod PZ is a field. So it is an UFD. So in this case it is true. But if you take from ZX to, let's say, Z root minus 5, where your f of x maps to f of root minus 5, then this is also in surjective ring homomorphism. And the kernel of this is x square plus 5. So this will be isomorphic. So this is an surjective ring homomorphism and Zx is an UFD. But we know that Z root minus 5 is not an UFD. So it is an UFD and it is not a UFD. So this is also not true in general. Is it okay? Shall I move on? Okay, so if you still feel any doubt, you just go through the notes, and if you still are not convinced, you can ask in the next session. So problem number 8. So let F be a field. Okay, then prove that the polynomial ring over F in one variable has infinitely many irreducible elements. So we all know that fx is an PID, right? And every PID is UFD. So fx is a UFD, is an UFD. So in this problem, we need to prove that whatever field you take, then if you take the polynomial ring over that field, then that ring must have infinitely many irreducible elements. So, if you take this field to be an infinite field, then this problem is very easy to prove, right? So if f is an infinite field, so can you see why? If f is an infinite field, then this is easy to prove. So remember that degree 1 polynomials are always irreducible over a field. So then x minus a is irreducible for every a belongs to f, and f is an infinite field, so there are infinitely many a, so there are infinitely many x minus a. So in case of infinite field, this is very easy to prove. But what happens in case of finite fields? Okay, let me write, but this argument will not work if f is finite. So how to prove this statement in case of finite fields? So I will do the proof, and that proof will work for both the cases, right? This I have just written for information. So for I will prove this by contradiction. So suppose fx has finitely many irreducible elements. So here f can be any field. It may be finite, it may be infinite, it does not matter. We are proving this in general. So fx has finitely many irreducible elements. Let's say p1 up to pn. Now take r equals to p1, p2 up to product pn plus 1. So this is also an element in the polynomial ring fx. and fx is a UFD. So this R has an irreducible factorization. So R, okay, let me write. So R must have some irreducible factor, and this is because fx is a UFD. So irreducible factor, let's say P, but we have only finitely many irreducible elements P1 up to Pn. So this P must be one of these Pi's. So P equals to Pi for some I equals to 1 up to n. Now P is a factor of R, right? So that means R equals to P times some R prime for some R prime in the ring f of x. Now use this equation. So this imply P R prime equals to P1, P2 up to Pn plus 1. But P equals to Pi. So that will imply you can take Pi common, and this will give P R prime minus P1, P2, Pi minus 1, Pi plus 1 up to Pn, and this is equals to 1. Now this belongs to f of x, this belongs to f of x. So product of two elements is 1. So that means this element must be a unit. So Pi is a unit. But Pi is irreducible element, right? So this cannot be unit. So this is a contradiction. Thus, fx has infinitely many irreducible elements. And in UFD, irreducible element can only be its prime element. So in a UFD, there are infinitely many prime elements. So this is basically the copy of the Euclid's proof. So Euclid proved that there are infinitely many prime numbers. So this is the same proof. So is it okay? Did you got the proof? Okay. So fx has infinitely many prime elements. Okay, so this is not part of the proof. Yeah, so problem number 9. Okay, so in the lectures we have saw that if R is a Noetherian domain, then uh, every element has factorization. That means factorization terminates in R. So this is one of the result which has been taught in the lectures. So this is not saying that Noetherian domain implies UFD, because for UFD that factorization has to be unique, right? So can you give an example of a Noetherian domain which is not an UFD? So let me write, give an example of a Noetherian domain which is not an UFD. So do you have any example in your mind? So this is not difficult. Whatever you have learned, this can be done from that only. So from the earlier examples, can you conclude something? Can you see from the earlier examples? Yeah, any answer? So we already know that the ring Z adjoint under root minus 5 is not an UFD, right? But is this an Noetherian ring? This is a domain, that is clear, because it is a subring of an integral domain. But can you prove that it is Noetherian? Yeah, anyone? So Z root minus 5 is basically Z adjoint x modulo x square plus 5. So this is quotient of a Noetherian ring. So quotient of Noetherian rings are Noetherian. So Z root minus 5 is a Noetherian domain. Okay, so this is not difficult. You just have to look for the earlier examples. Okay, now what about the other way? So we know that uh, PIDs are Noetherian rings. Now, can you say UFDs are Noetherian or not? So, every UFD is Noetherian? Is it true? So, let me write down as true or false. So, every UFD is Noetherian. Yeah, is it okay so far? So far, do you have any doubts? Okay, so try to think this. Is it true or false? So, do you know any non-Noetherian ring?
Sir, can we go like this? Every UFD is Noetherian, na? So, Noetherian being PIDs, so it
Uh,
implies like UFDs.
Noetherian rings are PIDs. Is it true?
PIDs are Noetherian, I think.
Yeah, PIDs are Noetherian.
Okay, okay.
So, PID implies Noetherian. But the converse is not true. That is very easy to see, right? So you can take ZX. It is definitely Noetherian by Hilbert basis theory, but it is not a PID. Okay, so let me put that also here. So PID implies Noetherian, but converse need not be true. So for example, you can take ZX. Yeah. So now come back to this problem. So if you go back to the lectures, there is an example of non-Noetherian ring. So you just take R uh, Z X1 X2 to infinitely many variables. So then R is a non-Noetherian ring, but R is in fact a PID. Sorry, UFD. So why R is an UFD? So this is because every polynomial. So if you take a polynomial in R, so this is just finite sum of monomials. So it will be look like some a I1 in x I1 power alpha 1 x in power alpha n, and this will be a finite sum. So that means f involves only finitely many variables. So eventually f will belongs to some uh, z x1 up to xm, right? So if you take any element f, that will belongs to some S1 up to xm. Xm is the, you can take the largest index of the variable involved in f, and this is in fact an UFD. So using that fact, you can prove this. So I'm not going to write the details, but this is true. So you just have to convince yourself. So the key fact is every polynomial involves only finitely many variables. That is the reason. Okay, so let's move on. So let's try to prove one more ring that is not an UFD. So prove that. Okay, before that, let's do one more easy one. So we all know that uh, R is a field that implies Rx is a PID, right? So that is something you all know, but the converse is also true. So let's write down. Let R be a ring, then R is a field if and only if Rx is a PID. So this is something very useful. So one side you have already proved in the lectures. So R is a field implies Rx is a PID, already done in the lectures. Okay, so I just need to prove the uh, converse part. So conversely, let Rx be a PID. So we need to prove that R is a field. So we need to prove R is a field, right? So to prove R is a field, what we need to show? So field means every non-zero element is unit. So we need to prove every non-zero element in R is a unit. Okay, so let's take a non-zero element in R. Let 0 not equals to A belongs to R. So we will prove A is unit. So consider the ideal I generated by X and A. So then I is an ideal of Rx, that is clear, but what is given is Rx is a PID. So this ideal must be a principal ideal. So I equals to generated by Fx for some F belongs to Rx because Rx is a PID. So that implies A belongs to ideal generated by Fx as well as x belongs to ideal generated by fx. Okay, for the time you just consider a. So that will imply a equals to fx times some hx. Okay, now you compare degree of the polynomials of the both side. So in the left you have a constant term, so its degree is 0. So in the right also the degree must be 0. So degree of fx times hx is 0, but this degree is actually degree of fx plus degree of hx. So that means degree of fx is 0, and so fx must be a constant polynomial. So let's say fx equals to d for some d belongs to r. Okay, so now x is also ideal generated by fx. Let's use that fact. Now x belongs to ideal generated by fx. So that implies x equals to d times some gx, because fx equals to d. So we can write it here. So for some gx belongs to rx. So here what we can do is, so both sides is are polynomials. So from both sides you just compare the coefficient of x. So, so you will get 1 equals to d times d prime for some d prime belongs to r. So this is by comparing coefficients of x from both sides. Okay, now 1 equals to d times d prime. So that means d is a unit. So that means d is a unit. And our d is equals to fx. So ideal generated by fx must be the whole ring. So that means ideal generated by fx, which is ideal generated by d, must be the whole ring Rx. So ideal generated by x comma a is the whole ring Rx. So 1 must belongs to this ideal generated by x comma a. So from this we can write 1 equals to x times some px plus a times some qx. So both sides are polynomials. So again we will compare the constant term from both sides. So here we have multiplied by x. So this will not give any constant term. So constant term will come from only this term. So this is 1 times 1 equals to a times some b. So for some b belongs to r, by comparing constant terms. Okay. So 1 equals to ab. So that means a is a unit. And that is what we exactly wanted to prove. So we have started with a non-zero element in R and we have proved A is unit. Thus R is a field. So is it okay? Okay. So this is something will be useful for the assignment problems. Okay. So I want to mention one more general version of this theorem. So let me put that as remark. So this theorem is about when the polynomial ring in one variable is a PID, right? But if we weaken the condition, like instead of PID, if we ask it is just a principal ideal ring, then what can we say? So let R be a ring, then Rx is a principal ideal ring if and only if R is finite product of fields. So that means R is isomorphic to some F1 cross F2 up to cross Fn, where Fi's are fields. So this is the most general statement which I know. So I'm not going to prove this because this proof is little bit involving. So you can just take it as an information. Okay, so let's move on. So problem number 12. So we all know that z root minus 5 is not a UFD, not an UFD, right? So how we have proved is, so we have taken 1 plus root minus 5 times 1 minus root minus 5, and this is exactly equals to 6. This you can write it as 2 times 3.
2 into 3.
Yeah. So then we have taken a equals to 6 and b equals to 2 times 1 plus root minus 5. So in the lectures we have saw that these two elements a and b does not have any GCD, right? But in UFD any two elements must have GCD. So I want to say that this statement can be generalized. So let P be a prime number such that P greater equals to 3. Okay, so I am avoiding the even prime. Then if you take the ring z root minus P, then this ring is not a UFD, is not a UFD. Okay, So I will not write the whole proof because it is exactly the same proof as you have done in the case of z root minus 5. So let me just write down the steps. So here, if you take r equals to 1 plus root minus 5 times 1 minus root minus, sorry, root minus p. So this r is basically 1 plus p, right? And p is odd because p is greater or equals to 3 and p is a prime number. So p must be odd. So 1 plus p is even. So this you can write it as 2 times some r. So then take a equals to 2 times r and b equals to 2 times 1 plus root minus p, and then try to prove that a and b have no GCD the same way. Okay, so you try to write down this proof. So if you feel any difficulty, you just come back in the next problem solving session. So till now you just try it on your own. Okay, so I feel I have done enough problems. Okay, so do you have any doubt, or maybe we can close today? So since we have some time, if you have any doubt, we can discuss now.